Okay, so we're talking about Ka calculations for weak acids. We know about Ka and Kb for weak bases. We know that if that value is very, very high, we have a very strong acid or base. And a very strong acid completely dissociates, or very nearly completely dissociates, so that there is nothing of the original acid left. It's completely dissociated into its ions. That's very strong. But for weak, similar to KEQ, for weak acids, we have this Ka value. So let me just remind you here, and this would be good, probably a good remembrance. It's a bit of a summary. The KEQ would be the products, the concentration of the products, C and D, okay, divided by the concentration of the reactants. Let's say that's A times B, okay, and that's of course for A, plus B produces or comes into equilibrium with C plus D. So you guys remember that, right? The KEQ, that's how the equilibrium constant is set up. And the key here is that A, B, C, and D, they're all of those concentrations can change. So they're like aqueous, they're dissolvable. The concentrations can change. If there's any solids in the mix, we don't include those because solids don't have a changing concentration, right? So remember that. Now, KSP is where we went next after that. And KSP would be more or less, we have let's say, AB solid, and that dissolves to A plus 2B minus. That's what it looks like there. AB, that's just a solid. So we'll just go AB, A plus B with the charges there. So let's say we have something like this. It's dissolving, and it's actually coming into equilibrium with its solid here. And so we just take the concentrations of A plus and we multiply it by concentration of B minus. And you remember this, of course, if there's a 2 or a 3 as a coefficient, that's a cubed or a squared as an exponent. And this is what happens. And the reason why we don't include AB is because it's a solid. So for the same reason, we wouldn't include it in the KQ. Now, for the Ka, and I'll just use Ka as an example. Kb would work for a base, but let's just focus on Ka, one type of calculation. So Ka, let's say we have AB, and this is aqueous. It's an aqueous acid, okay? And so AB is going to, again, dissociate into A plus B minus. So this is what we have. But it's going back and forth, and of course these are aqueous as well. So this is the Ka is very similar to the KSP, but different in that this is not a solid. This is an aqueous. So it's more like, this Ka is more like the KEQ, because the reactant here is aqueous, so the concentration can change. All right? So if we have a weak acid where we have a Ka value that's listed, it's a very small Ka value. It's not high, it's small, or at least there's any kind of number, we can do this calculation. If it's just the Ka is very high, then this is virtually gone, right? But the Ka looks like this. It's the concentration of A plus times the concentration of B minus. But then, like the KEQ, you do have to include here the remaining or the reduced whatever concentration of AB. Okay? And so for your Ka values of weak acids, you can't just multiply these. If you're given an initial concentration, you have to include that initial concentration in the Ka expression. Okay? And that's one important thing we don't want to miss there. Again, this is not solid, so we would include it in this expression. It's at equilibrium, there are products, and there are reactants. All of these concentrations are subject to change. So in your textbook there, page 656, Glencoe text, Chemistry, Matter, and Change, calculating Ka from pH. Here's an example, and I just want to highlight this because this is really, I think, the only place where they sort of get into this type of calculation in this textbook. So here we have HF, that's hydrofluoric acid, and it breaks down to H plus and F minus ions. Okay. Now it's a fairly strong acid, but there would still be small amounts of HF remaining, and technically that very, very small amount of HF could be included in the Ka expression. Now, before we get into any of this here, If we have a very strong acid, think about this. The concentration of the original acid would be super small, close to 0. When you divide by a number that's close to 0, the whole value is very, very large. So in very strong acids, when you divide by a concentration that's near 0, you're getting a very large number, okay? So we'll want to remember that. But for weak acids, maybe this number is not that small. And so then it becomes a real factor, and we have to consider that. And then that's where we get a Ka that's not as large, right? Or if we have, 0.8 or something, like that's getting pretty big now. So we have to include that. We can't just omit it. Okay, any questions so far? Okay, so let's take a look at this from the textbook. So suppose you measure the pH of a 0.1 molar solution of weak acid HF and found it to be 3.2. Would you have enough information to calculate Ka? Okay, so here's calculating Ka. And let's read what it says, because this is what we want to focus on here today, and we'll extend this in the next example. From the pH, you could calculate H+, ion concentration. Then remember that for every mole per liter of H+ ion, there must be an equal concentration of F ion. So the pH would give you this concentration right here, and then because this is a 1-to-1, you could find F. Okay. So what about the third HF? So this does have to be included in the Ka if there's any kind of value at all. If it's not 1, it really should be included. The concentration of HF at equilibrium is equal to the initial concentration of the acid minus the moles per liter of HF that dissociated. Okay, so if you remember doing ice charts with equilibrium, because Ka is kind of like equilibrium, this is sort of like the ice charts, right? So if you remember KEQ, or let's say that we have X here. We don't know what this is, concentration, and we have X here. Okay, then HF. Let's say that we have 0.1 molar, right? 0.1 molar HF. Then in this Ka, we would have X here, and then we'd have 0.1 minus X. So do you remember this kind of thing? Now, if we knew the Ka, we would have a value that we could put in here, and we could solve for X. And that's sort of like the questions that I want to get to, and the questions that you're going to really know how to do here. But this is, I'll just show this again, that the initial concentration of the acid is going to be important in the Ka expression. Okay, so let's do an example from your textbook here. And you can look in your textbook. You can write down as much of this as you want. I don't have this in your copied notes here today, but probably will be in for future classes. So let's see here. Oh, I feel like I'm missing the first part here. Give me a second. So on page 657, example problem 5 says this: calculate Ka from pH. So we'll do this type of question first, and we'll do a second type of question to finish off this little mini lesson. So calculate Ka from pH. Okay. Formic acid is used in a process latex tapped from rubber trees into natural rubber. The pH of a 0.1 molar solution of formic acid is HCOOH is 2.38. What's the Ka? Okay, so it's a weak acid. We've got the pH here of this concentration of solution. So let's calculate the Ka. So you're given the pH of the formic acid, which allows you to calculate the concentration. So again, the important thing is to be able to understand what the dissociation equation is, or what the equilibrium sort of is with this acid. It's a weak acid, so you have the full acid there at the beginning, and then it breaks up at least partially into H+ ions, and then your HCOO- ions. So there's a partial dissociation. That's important to see and to understand that. It's also important to know it's a 1-to-1-to-1 ratio there. So the balanced chemical equation shows that this concentration equals the concentration of H+. So this is, like I said, 1-to-1 there. So the concentration of unionized HCOOH is the difference between the initial concentrations of the acid and the H+ concentration. So if this is pH 2.38, concentration is 0.1 molar. Let's solve for the unknown. So what we want to do first is, you remember what you do if you're given pH and you want to find the H concentration? You go 10 to the power of negative 2.38. You take the pH, throw a negative in front of it, and then put it in the exponent position. That's how you get the concentration of your H plus there. So in this case, what's it going to be? It's going to be 4.2 times 10 to the 3. Negative 3. And that's moles per liter of H plus. Okay? So that's also going to be the concentration of the second ion there too, this HCOO minus. So they're both that way. And so the Ka, let's take a look at the Ka. So you need the concentration. I'll zoom in for you. That's getting a bit small. We need the concentration of H, which we just found. Concentration of HCOO minus, which we also just found, are the same. But we need to find the concentration of the original Ka. And for that one, what we do is take the original concentration here and subtract the concentration of the H plus that we found. Because remember, in this equation, this is going to be 0.1 molar minus some X value, because this is X and this is X. So we need to include this, right? And that's going to be our pattern if we want to find, later want to find an unknown concentration there of H plus. So to find the Ka right here, we go ahead and do that. Put in our concentrations. And then this is the big thing right down here. You have to have a concentration underneath there as well to solve for the Ka. So when you divide by that, then you get your Ka. Okay? So before we get to the textbook questions on this matter, okay, because these questions are practice questions for solving for Ka and so on. The next part of this lesson that I want to focus on as well is, how do we solve for a concentration, okay, given an initial concentration of the acid and given the Ka. So we're going to use the same sort of setup right here, okay, the same sort of setup, and then we're going to be able to find concentrations. Okay, so here's a question where we're going to solve for concentration in a weak acid solution. So we have a weak acid of formic acid here, and we have a Ka. Now this Ka is right on the cutoff line, really, right, of what is sort of strong and what is weak. Is this producing a lot of ions in solution? Is it producing a very small amount? This is right at the cutoff line, okay? So anything 10 to the negative 4 or less would be considered very, very small compared to a concentration like this. So what I'm saying is that if the Ka is, 4 or 5 multitudes or magnitudes of 10, smaller than the given concentration, we're going to be able to omit the small amounts of ions that are going to be produced compared to this original concentration. And you'll remember this kind of example once we get into it, okay? So this is right on the cusp of, is this a strong acid or a weak acid? What's it doing? It's still negative 4, so it's still fairly weak. All right, so get into our calculations. Okay, so the first of all, formic acid is HCOOH, and that's going to mix with water, and it's going to come into equilibrium with the hydronium ion. Okay, this is the hydronium ion, and HCOO negative. So we have, we're going to have aqueous, or sometimes you'll see this acid as being liquid. It still dissociates, so the concentration could still change. Water is not really involved in this so much, because it's liquid and it doesn't change concentration, so this is not going to be in the Ka. But again, this is aqueous and this is aqueous. All right. So the Ka is going to be very similar to the KEQ. So we're going to have concentration of hydronium times, and is this balanced? I guess it's balanced, right? Concentration of HCOO negative. But then what we're going to have to do is we're going to have to divide it by the concentration of HCOOH at equilibrium. And water is omitted because its concentration doesn't change. All right. So that's what we have, and we also know that this Ka is 1.77 times 10 to the negative 4, which is still fairly small. Weak acid's fairly small. Weak acid. Okay, so what we're trying to do is trying to solve for the hydronium ion concentration. This is what we're trying to solve for. So we have to figure out how we're going to represent these three things right here. And we're going to have some kind of variable or unknown. So we notice that this is a 1 to 1 to 1 to 1 ratio, right? Because we said that was a balanced equation, 1 to 1 ratio. So as this acid disintegrates or dissociates and breaks apart, it's going to form the same number of moles of this and this. So whatever breaks off of here, okay, a little amount is going to dissociate the concentrations of the ions, 1 to 1 ratio here. So this is going to start off as, let me just make a little space here. That was awesome. Let's try again. So this starts off as 0.1 molar, right? And we're going to this is going to be decreased slightly, and so this is going to be producing some unknown concentration here, and because it's a 1 to 1, some unknown here. Okay? Now at equilibrium, this 0.1 molar is actually going to be decreased by that X amount, right? So remember how this is very similar to KEQ? Okay? So by rights, the full equation now should look something like this. It should look like X here times X here, right? Divided by 0.1 minus X. So very similar to your ice charts, KEQ calculations. How many of you remember that? You remember that? Okay, all right. So remember, weak acids and bases are a lot like KEQ. Now, what I was mentioning before, because this is a weak acid, there is a shortcut in the math. So obviously, we can solve for this right here by multiplying both sides by 0.1 minus x, and we're going to get a quadratic. Remember that? And for those of you that are really into math and remember the quadratic formula, you could use the quadratic formula to find x. As it so happens that this 10 to the negative 4 is sort of the cutoff for most concentrations. Now, if this was 0.00001, then they would be pretty much the same, and we can't omit x. But because this is many more times bigger, this concentration, the original one, it's kind of like, taking $1 billion and losing $1. Well, if you have $1 billion and you lose $1, you don't really notice it. You still pretty much have $1 billion. So if this number is 10 to the minus 4 or lower, that means that this x compared to this original concentration is going to be insignificant. We can't get rid of these x's up here, but we can get rid of this minus x down here, which is just going to make the math real easy, and it's not going to sacrifice too much precision. So that's an important thing to remember to make your math a little bit easier. Okay, so now what we have is this number equals x squared over 0.1. That's going to be really easy to solve. We multiply both sides by 0.1, or you like your cross multiply there. So this is 1.77 times 10 to the negative 5 equals x squared. We'll take the square root of both sides. Square root of both sides, and what do we get? We get x equals 4.21 times 10 to the negative 3. Did that on your calculator, that's what you should get. Okay, so very similar to KQ, this is Ka for weak acid, and when you get to this point, you should double check and reread your question over and make sure that you know what the question is asking for. What is the hydronium ion concentration? So we're looking for the concentration of this right here, which happens to equal X. So you finish off your question by saying H3O plus concentration is 4.21 times 10 to the negative 3. And when we do these calculations, this is in moles per liter. All right. And then, of course, from here, you can calculate pH really easily. Negative log of this is the pH. You can calculate pOH or OH concentration using kW, that sort of thing. All right, any questions about this example right here? Okay, so here's a question for you guys to try on your own, very similar to the question we just did. So take a few moments, give that a try, and I'll reveal the answer here momentarily. Okay, so let's give this one a try here. So hydronium ion concentration. Sure you guys can see what I'm doing here. Hydronium ion concentration in 0.02 molar HClO. Okay, Ka 2.88 times 10 to the negative 8. Okay, so we have HClO. Now, HClO. So hydronium ion and hydrogen ion are different. Hydronium is H3O plus. Hydrogen ion, if the textbook or you're talking about hydrogen ion, that's just H plus. You wouldn't have to include the plus H2O, but because we're talking about hydronium ion, hydronium is this one, H3O plus, right? So that's why you have to have the water there, because this is hydronium, technically. And then what else do we have here? We have ClO minus. So why do you need to do that? Well, you just need to know whether we have a 1-to-1 ratio, or maybe we have a 1-to-2 ratio, or whatever. Most of these acids are gonna break up. One hydrogen is gonna come off, so it's gonna be, pretty much 1-to-1 ratio here. So that's what you want to just double check. So 1 to 1 to 1. I think everything looks good there. Okay. So the Ka here, the expression is going to be H3O plus times ClO minus all over. We don't include the water, but the HClO. Okay. So we have a small concentration, but we also have an extremely small Ka value. So whatever breaks up here, this is going to be 0.02. This is going to be reduced by some unknown concentration, and that's going to be the same concentration of these two ions generated, 1-to-1, X to X. And so we kind of have this set up similar to the last question. Now, this is very small. Even though this is small, this is still many, many magnitudes of 10 less. So when we put our equation together, okay, you're going to put X up here for each one of these. And on the bottom, we have 0.02. And that's going to be technically minus X. But because this minus X is super duper small, it's kind of like having $1 million and you lose 10 cents or something like that. You still pretty much have $1 million. So in the math calculations, subtracting this by something that's many, many more decimal places way down here, it's not going to change. So you can drop the minus X there. Again, this is a small number, and so we can drop the minus X. So this becomes pretty straightforward. We cross multiply here up to there. We know that's X squared. And so we have X squared here equals, and we'll do this on the calculator. You guys have this done already, hopefully. There's my calculator coming. There we go. Oh, I hit it twice. Look at that. C and double. Exit. So 2 point on. Okay, get out of here. 2.88. Use your exponent button there, the scientific notation button, times 10 to the negative 8 times 0.2 equals, okay, 5.76 times 10 to the negative 9. And we're going to take the square root of that, aren't we? The square root of the answer. 7.589 times 10 to the negative 5. Did you get that for an X value? So we'll go 7.59. Oh, it's 0.02. I just put 0.2. Thank you. Let's try that again. Yeah, good call. Entry. Yeah, if you have a calculator like this, sometimes you can kind of recall your entries there. So 0.02, 10 to the negative 10, good. And then we'll square root the answer. 2.4 times 10 to the negative 5. Did you get that? Is that what you got? Awesome. Okay. So x equals 2.4 times 10 to the negative 5. Great. Good job. That's a 2. Okay, so is that the answer? Well, do we have to do anything more? Again, look at the question. What's the hydronium ion concentration? Hydronium ion is represented by X. We just found X. So H3O plus. And please don't forget your charges. Some of you are still forgetting your charges. H3O is different than H3O plus, so make sure you put your charges in there. 2.4 times 10 to the negative 5. Also make sure you have your units. That would be moles per liter. Okay, excellent. I'm going to give you one more here, one more to do, and then we'll be done this lesson here. One more to do. Oxalic acid, you're probably going to have to look that one up. Okay, look that up. What does that look like? Do we have a 1-to-1 ratio with its ions and so on and so forth? So go ahead and give that one a try. See what you can tell me about oxalic acid. Okay, so here's your oxalic acid. Just for the video here, I'll snap that in. Okay, there we go. So of course, to make this hydronium, we'll add water. And we do see it's all 1-to-1, so we're good to go there. So, okay, so here's the solution for this question here. You can check that. So yeah, the oxalic acid dissociation equation there with water produces your hydronium and the other ion, and so let those equal X. Use your initial concentration, right? Now, if you guys notice, when a concentration isn't given, and you're just given the Ka, and you're asked to find out what the dissociation would be, what the concentrations would be, it's kind of like this doesn't exist, or like it's 1, right? So this concentration, if it's less than, like if it's less than 1, I guess it would make sense that it's going to produce fewer ions, right? If it's highly concentrated, it's going to break down the same way, but it'll end up producing more ions. So that's why you have to include the original concentration. It's going to change this number a little bit, see, because we multiply the Ka value by whatever the concentration is. So that's the big difference. If you're given initial concentration, that's why you have to include that. A higher concentration, you're going to have some more ions produced. Lower concentration, you're going to have fewer ions produced, even though it dissociates sort of the same way. So if you're given an initial concentration, make sure you include that in your Ka. And yeah, that's sort of the lesson for today. Ka concentration. So these are questions from your textbook 32 to 34. And then these questions that we really did together here are questions you want to add to your notes for your hand-in assignment for you guys for this class. Okay, any questions? Awesome.